My name is Phil Kaaret from the University of Iowa, and I'm going to be talking about black holes of all sizes. So my outline for today is given here. It's a family-friendly thing, as advertised. First, we're going to talk about detecting black holes, and then sizes of various black holes that we know or sure exist in the universe. Then we're going to talk about a relationship between black holes and galaxies. And then we're going to get into what I actually spend a lot of my time doing, trying to find out whether or not they're actually something called medium-sized black holes. So the first question is, how do you detect a black hole? How do you detect a black hole? Okay. No, I was literally just setting up the joke. It was a rhetorical question. But that was a better response than that slide usually gets. We detect black holes, since they are indeed black, by looking at their effect on other things nearby, either stars or gas. And we'll actually talk about both cases. This here is a picture of the center of our own Milky Way galaxy, okay, where Andrea Ghez of the University of California in Los Angeles took a telescope, actually the Tech telescopes that you might know out on Hawaii, pointed them at the center of the galaxy, and then took pictures every so often. What's counting off here is actually year and then fraction of a year. Okay? These, she actually made this image in 2004. That's why it goes up to 2004 and stops, and then the rest of it is prediction. And what's shown here are individual stars that you can see moving around right very close to the center of our own galaxy. Okay, just for reference, this little tick mark over here is about 3 light days across. Okay, and you can see the stars moving around. And there's no star here where they seem to be moving around. I mean, we actually drew in a little star-shaped thing, but you don't see anything in the images. But there must be something there that's causing these stars, for instance, this one over here, SO16, it moves in towards the center of the galaxy and then suddenly makes this huge sharp turn. Completely makes a U-turn, goes all the way around. Okay, and right when it's making that U-turn, it actually is going. The entire star is going at 1/30th of the speed of light. So there has to be something tremendous right there that's causing that star to move around like that. Okay, if there wasn't anything there, the stars would just continue on straight lines all the way across. And what's actually there is a black hole that weighs about 3 million times the mass of our own sun, or something I'll call solar masses. So this is actually the most direct evidence we have for a black hole, the supermassive black hole at the center of our own galaxy. We can actually see the stars move around, influenced by the gravity of that black hole. Okay, unfortunately, that's the only case where we can see the stars moving around and actually take pictures like this. Other galaxies are too far away, and there are things called stellar mass black holes that are about the mass of our sun, or maybe 10 times the mass of our sun. But they exert a smaller influence. We can't actually see their star, any stars orbiting them, move around. Okay, so now let me ask you a question. If we can't see it moving around on the sky, is there still any way we can tell an object is moving? No. Okay, and I prefer answers from those under 15. Well, let me ask you a question. So this is my iPod. Can you guys in the back hear that? Is it moving? Now is it moving? Now is it moving? Yes or no? Is it moving? It's moving right now? Now? So you can't see it, but you can tell whether or not it's moving. And why is that? Okay, you use something called the Doppler effect. And so what my gizmo is doing is putting out sound waves. And if the object is moving towards you, the sound waves get all bunched up together. Okay, and bunched up sound waves, the pitch that you hear for sound is determined by how far apart the sound waves are. So if the sound waves are close together, you hear a high pitch, and the sound waves are far apart, you hear a low pitch. So if I take my iPod out again, okay, as it's moving towards you, you hear it higher. As it's moving away, you hear it lower. Everyone believe that? Oh, you guys are too easy. Come on. Okay, well, sound doesn't travel through space, except it does sometimes. But the Doppler shifts also works with light. Okay, you know that there are different colors of light. For instance, for astronomers, there's mainly red and blue light. We actually don't get that fine into details. Okay. And red light corresponds to things with photons with long wavelengths, and blue light, or violet light, corresponds to light with short wavelengths. So if you imagine the same situation that you had before, in this case, the little person is moving in this direction. Fortunately, the person who drew that slide drew it differently from the previous one. But in this case, the person's moving in this direction. If you were looking at that person coming towards you, the light would be slightly bluer. If you were looking at that person moving away from you, the light would be slightly redder. So we actually see black holes in our own galaxy by looking at the stars orbiting around them. That's what's shown in this picture over here. You imagine there's a black hole there, there's a star that orbits around the black hole, and when it is moving towards us, the light gets blue shifted. When it's moving away from us, the light gets red shifted. And that's actually how most of the black holes in our own galaxy, well, actually, most of them are discovered a different way, which we'll get to later. But that's how we actually go ahead and measure the masses of the black holes in our own galaxy. We see a star orbiting around them, and we can measure that orbit of the star. Even though we can't see the star move back and forth on the sky, we can see the light from the star get slightly blue shifted and slightly red shifted. Okay, and if you study that long enough, you can figure out how massive the black hole in the middle has to be. Okay? You can also do this for black holes that sit inside other galaxies. This actually is a picture here of a galaxy called M84. It's a so-called elliptical galaxy. It doesn't look like our nice spiral Milky Way. It's actually just a ball of stars. But at the center of it, there's a black hole that's a few billion solar masses. Okay? And what this image over here is, so first, this is a picture of the galaxy taken with the Hubble Space Telescope, and then look at the little light blue slit. Okay? What these guys did was take an instrument on the Hubble Space Telescope that splits the light according to its color into what we call a spectrum. So this picture over here is the image of the galaxy along this same slit here. So this dimension of that image is a position along the position within the galaxy along that little slit. But this direction over here isn't an image of the galaxy. It shows how much light there is at different colors. And you can see that if you look right at the center of that galaxy, there's a blue band over here and a red band over here. What does that mean? That means over on this side, the stars are moving away from us, and over on this side, the stars are moving towards us. And how could that happen? Sorry? Yeah. If there's a massive object sitting right in the middle there, you could have stars circling around. Okay? And on this side, the stars are coming towards us. On that side, the stars are going away from us. So this is actually how we measure the masses of black holes in other galaxies, not by looking at just one star moving around, but by looking at a whole bunch of stars moving around. And you can see from this picture, we can't even distinguish the individual stars, but we can still see how they move all together, indicating there has to be some massive dark object sitting in the middle. Okay, so people have made a lot of these measurements. In fact, I think one of the Hubble Space Telescope's greatest legacies will be the fact that we actually couldn't measure the masses of these black holes in other galaxies until that instrument was put on the Hubble Space Telescope. We just didn't have anything good enough to do it, to see really the fine motions of stars. Okay, but a lot of these measurements have been made, and there are two types of black holes that essentially every astronomer will agree to. They're what we call stellar mass ones. Okay, and this funny little symbol here means M is for mass, and this is the symbol for the sun. So that means solar masses. So there are two types of black holes that we know. Okay, one that we call stellar mass, and they have masses. The lightest one weighs 3.2 times that of our sun, up to about 20 or 30. Okay, these kinds of black holes are formed by the collapse of an individual star. In fact, in a supernova explosion, which if you come next month, Randy McIntyre will be talking about it. We've directly measured the masses of about 30 of these, but we actually from that extrapolate that there are about 100 million of them in the Milky Way. Don't ask why. Okay, the other kind of black hole that we find are the so-called supermassive ones. They weigh anywhere between 100,000 and 1 billion times as much as our own sun does. And they're always found right at the center of a galaxy. And essentially every galaxy has one. In fact, there's a countable number of exceptions. 2. Where people have really gone and looked hard enough and actually not seen a black hole that should be sitting there in the center of a galaxy. So these are two types of black holes that we know about. In fact, that's an important lesson. If you take away nothing else from this talk, that's enough. But there's a very interesting relationship between these black holes that sit at the center of galaxies and the galaxy themselves. Okay, so this is a picture. Does anyone actually know what it is? And then the adults can answer this one too. Yeah, this is Andromeda, M31. It's our nearest, it's the nearest galaxy that's about comparable in size to the Milky Way. It's actually very similar to the Milky Way. It's probably somewhat, the stars tend to be somewhat older. It's about the same mass. In fact, it kind of goes back and forth which one's bigger. But this is more or less what our own galaxy would look like from the outside. So the different parts of a galaxy are, well, this is the disk. That's what everyone thinks of when they think of a galaxy, beautiful spiral arms like the Milky Way has. That's only one part. That's what the astronomers call the disk of a spiral-type galaxy. There's also the halo, which are all these stars around here, a huge field of that tend to be very old stars that basically form a ball that the galaxy sits inside. And then there's something called the bulge. Okay? And you can see in the middle of M31 or Andromeda, there's basically a ball of stars here. Those stars are also old. Most of them were formed when the galaxy itself was first formed. Okay? And there's a very interesting relationship. So what people have done is for a number of galaxies, they've gone and measured the mass of the supermassive black hole sitting in the center here, and then measured how fast the stars are orbiting around inside the bulge. Okay? If you'd asked me 15 years ago, I would have said those two things are completely unrelated. Because why should the black hole at the center have anything to do with the rest of the galaxy? The black hole's tiny compared to the rest of the galaxy. But this is the only plot I'll show, so those who don't like math or plots, it's okay, we're over it now. So what this shows is every dot is a galaxy. And for every galaxy, 2 measurements have been made. This sigma is how fast are the stars orbiting around in the bulge of the galaxy. And the M black hole is, what you might guess, it's the mass of the black hole sitting in the center. And you can see that those two things are related. Okay? If you have a bigger mass black hole, you actually have the stars orbiting around faster. And it's not because of the mass of the black hole. The mass of the black hole is not nearly enough to keep these stars orbiting around that fast. Okay, and if you have a low mass black hole, you have the stars orbiting around more slowly. What this means is there's some fundamental relationship, which we actually don't understand. But when galaxies get formed, they also form these supermassive black holes at the center, and they're not independent processes. This graph, because there's this correlation, shows that those two processes are intricately linked. So even in our own galaxy, somehow the formation of our own Milky Way galaxy is closely tied with the formation of its supermassive black hole at the center. Okay, and if you come back 10 years from now, I hope to give you a very good explanation as to why that's true. But I can't do it right now. This relation was unknown 15 years ago, and there's a lot of debate as to why it's caused right now. But it's telling us something important about how galaxies form, and hopefully we'll be able to figure it out within the next 5 or 10 years. Okay, so I went back to this one, and I told you we know about black holes that weigh up to maybe 20 or 30 times the mass of the sun, and ones that weigh 100,000 times. There's a big gap there. Okay, how many of you feel that there should be at least something sitting in that gap? Yeah, good. Fortunately, science is completely undemocratic. But okay. So there's a question about whether or not there's anything in between those two ranges, these little sun-sized black holes and the supermassive one. Well, it's sort of important to note that you can't form such a, say, if you want to make a 1,000 solar mass black hole, you can't make it in the same way you make a 10 solar mass black hole. Because a 10 solar mass black hole, we know how to make it. You take a star, you let the star burn out to the end of its life, it supernovas, the core at the end implodes, and you get a black hole there. But you're clearly not going to get a black hole that weighs any more than the star weighed to begin with. And there aren't any stars that weigh more than about 100 solar masses. In fact, most of them lose most of their mass over the course of their lifetimes, or a fair fraction, like half. So you can't form a 1,000 solar mass black hole, or even 100 one, in the collapse of a normal star. Okay, you could form them in mergers in star clusters, which I'll talk about in a minute. Or, interestingly, the very first generation of stars formed after the Big Bang were much larger than the ones we have today, because they were formed almost completely out of hydrogen and helium, because the other elements like oxygen and carbon and nitrogen hadn't been formed yet. You actually make those in stars. So clearly you're not going to have any of those elements before you've made stars. And the first stars were actually very massive. So if you could find a 1,000 solar mass black hole, it actually might be a remnant of the very first stars that formed after the Big Bang. Okay, and so why is it interesting? These intermediate mass black holes may also be an important step in the formation of supermassive black holes. I told you we know that supermassive black holes exist. It's very confident that they exist. But we actually don't know how to make those supermassive black holes. And most people's theories can't make them fast enough. You see supermassive black holes even when the universe was very young. But you don't have enough time to say the most natural way to make a black hole massive is for it to suck in gas. But you simply don't have enough time to suck in gas if you start with a stellar mass black hole and try to suck in enough gas. You need something to kickstart the process. And intermediate mass black holes have been brought up for decades as a potential way to do that, except there aren't great ways to make intermediate mass black holes in the first one. Okay, related to this, they could be generations of first stars, and third, they're cool. Okay, a new kind of black hole is just, it's cool. You guys must agree because you're here. Okay, so is there anything intermediate? Is there anything between? Well, I told you there was this relation between how fast the stars orbit around and the mass of the black hole. So what you might try to think is, well, maybe galaxies, the stars and their bulges, all orbit around really fast. But maybe there's some other kind of object out there that looks like a bulge, but the stars orbit around more slowly. In fact, there are such things, and they're called globular clusters. They're these spherical balls of stars. Okay? And it turns out there's one particular globular cluster named Mayall-2, or G1. It's actually a globular cluster of Andromeda. It's not a globular cluster of our own galaxy. Where if you look at how the stars move around in here, this group over here, Carl Gebhardt from the University of Texas, actually estimates that there's a 20,000 solar mass black hole in there. The most natural way to explain his data is there's this 20,000 solar mass black hole. The problem with this is that you can also interpret the data in other ways by having a collection of, say, a neutron star, something else that's dark and massive. And you can't exclude the idea that there would be no black hole at a better than 97% confidence, which is good enough for normal people, but not nearly good enough for scientists, unfortunately. So that's probably the best case where we've tried to look for an intermediate mass black hole by looking at the motions of the stars. Maybe what we have to do instead is go back and think about, well, how can we just look for black holes in general? And maybe if we can find a good way to search for black holes, we'll find some unusual cases that could be then intermediate mass black holes. So how would you best look for a black hole? Good. No one has an answer. Instead, let me ask an easier question. How do you best look for a human? Okay, and now I need the light in the back off. And okay, everyone relax, because I'm going to make the room totally dark. How do you look for a human in the dark? Okay, no, now we're going for the under 15s. By the light of the TVs. Okay, now I'm going to have to turn off the monitors. Thermal energy. And how do you actually look for thermal energy? Now I'll have to turn the monitors back on. I can look with this thing over here and see all of you. And I could do it even if all the lights were completely off. Chair's blocking that. So how does this little camera work? Why do you guys look so funny? And why can I actually tell who has the flu? So we already talked about red and blue light. But the part of light that you can see with your eye, or I can see with my eye, is tiny. You can see on this spectrum over here, red is over there and blue is over there. The visible part of light is actually a tiny little piece of the total spectrum that light can be produced. Light instead goes all the way from radio waves down here that have very long wavelengths. This is the scale of wavelength of a radio wave. Okay, they also actually get as short as humans. Then microwaves, excuse me. The microwaves that you use to heat stuff in your microwave, or the wavelength is actually about as long as your pinky. Okay, infrared gets shorter. The visible light here is, very short. And then as we go to ultraviolet X-ray, the wavelength gets shorter and shorter and shorter. In fact, gamma rays have wavelengths that are only as long as the size of the nucleus of an atom. Okay, but the interesting thing about this is that wavelength actually corresponds not only to colors that you can't even see, redder than red or bluer than blue, but it also corresponds to energy. A blue photon has more energy than a red photon. And a hot object tends to have more energy per particle than a cold object. So wavelength also tells us about temperature. Okay, the surface of our own sun is about 6,000 degrees Kelvin. Okay? So it makes visible light right here. But how hot are you in terms of kelvins? Well, you're about 300 degrees Kelvin. Okay? If any of you don't want to go to school tomorrow, just wake up and say, Mom, my temperature is 300 degrees. I can't go to school. She'll probably take you to the emergency room or use you to light a match or something, or a piece of paper. Okay, cooler objects than the sun, like human beings, actually make infrared radiation. Your body's constantly pouring out light. It's just you can't see it. You have to use this funny infrared camera to see it. But even in the dark, you can see these things. Okay. On the other extreme, so now we have this idea that wavelength actually corresponds with temperature. Okay, so now we just have to figure out, well, what's the temperature of a black hole? Okay, I have to admit, someone called me asking if they should bring their fourth grader, and I said, yes, it's very family-oriented and he'll get something out of it. I actually spent almost 5 hours trying to explain to you how to calculate the temperature of a black hole. But I've decided instead you'd have to enroll in my graduate high-energy astrophysics class next semester. So I'm just going to tell you. Okay. Well-fed black holes actually get so hot that they're a few million degrees Kelvin. Okay? And I'll argue it like this. The temperature is basically a measure of how much energy you have in how much space. The total amount of energy doesn't matter. It's the energy per cubic centimeter, the energy in a certain volume. Okay, so black holes win on two fronts. First, they release a lot of energy. Well, in particular, they release energy if they're being fed gas. Of course, a black hole sitting by itself doesn't release energy. They're also very small. A solar mass black hole is only 30 to 100 miles across. So not only is it releasing a huge amount of energy, releasing thousands of times the amount of energy our sun does, it releases it in tiny space. It's like you took the entire sun and condensed it down to the size of Chicago. You think it would get hot. Okay? And that's exactly what happens. So we see black holes, when they are being fed. So typically, for a stellar mass black hole, what we see is a black hole only when it has a companion star. The black hole actually pulls gas off the companion star that forms a disk as it spirals down in. Okay? It forms a disk for exactly the same reason that a little whirlpool forms when you let the plug out of your bathtub, rather than the water just going straight down. Okay? As the gas falls down in towards a black hole, it gains energy. For instance, if I try to break this piece of chalk, will that take energy? Okay. But now I'm going to break the piece of chalk into lots of little pieces. Where'd the energy come from? Yeah, it was actually the gravitational energy of that piece of chalk falling down. It had less energy when it was at the top of the arc. It gained energy as it fell down towards the Earth. And then when it hit the floor, that energy was converted into a different form of energy. That energy of motion was used then to break the chemical bonds in the piece of chalk. In the same way, a black hole. You have a little blob of gas over here. It falls in towards the black hole. It gains energy, just like the chalk gained energy while it was falling down. Okay? And then it hits all the other little blobs of gas that have also fallen in towards a black hole. And that energy that gained from falling inwards now gets converted into heat. Basically, the blobs of gas hit each other and heat each other up. They convert their energy from falling into energy of random motions, which is temperature. Okay. Excuse me. And so the black holes get so hot, the inner parts here, the disks around the black holes get so hot, up to a few million or even 10 million degrees Kelvin, that actually the disk glows. It doesn't just glow in the infrared or in the visible, it actually glows in the X-ray. So instead of this little box, we then need an X-ray telescope. Okay, and I'm going to then tell you another thing about black holes, is that bigger black holes can actually be brighter. So now we've made this idea that black holes are fed by gas falling inwards. Okay, by the way, I drew this myself, so if any of you are an artist and want to improve on my drawing, you should email me afterwards, because I'd really like a nicer looking version of this. Okay. So imagine your little blob of gas flowing in. Okay, there are two forces acting on you. One is gravity that's pulling you in. Okay, everyone will give me gravity, right? The other force is actually pressure of the light pushing you out. Okay, because imagine here, this is the disk surrounding a black hole. This is your blob of gas. A photon comes out here and hits that little blob of gas. It's just like it got hit by a BB, that the photon, the light, actually gives a little push outwards to the gas falling in. Okay. So now let's imagine a situation where we start off with, we're feeding the black hole gas, but the black hole's dim. In that case, no problem. The gas just flows straight in. Now let's turn up the brightness of the black hole a little bit. There's more light coming outwards, so there's going to be more outward pressure on each little blob of gas. That's actually what we call radiation pressure. The radiation pressure goes up as the radiation goes up, of course. Now let's keep turning up the brightness of the black hole. What's eventually going to happen? The black hole's eventually going to get so bright that the radiation pressure is actually bigger than the gravitational force. And what's going to happen then? Is the gas going to fall in? No. If the black hole gets that bright, the gas is going to go out. But then what's going to happen? How was the black hole making all the light in the first place? No, it was by eating stuff. Very good. The black hole has to have the gas flowing in to make the light in the first place. So there's actually a maximum brightness the black hole can reach. If it gets any brighter than that, it shuts itself down. Okay? And since the gravitational force depends on the mass of the black hole, that actually means that bigger black holes are brighter. More massive black holes have stronger gravity, so they can pull in gas even when they're more luminous. And so there's actually a relationship called the Eddington luminosity, after Sir Arthur Eddington, whose other claim to fame was confirming Einstein's theory of general relativity by taking a picture of the sun during a solar eclipse. And it turns out that there's a certain amount of brightness. A black hole can get to 30,000 times the luminosity, and what was this symbol here? The sun. So that's the lumina, 30,000 times the solar luminosity, if you have a 1 solar mass black hole. And clearly, and that goes up. If you have a 2 solar mass black hole, it can get as bright as 60,000 times the brightness of the sun, the luminosity of the sun. If you have a black hole that's 10 times, it can get up to 300,000 times the luminosity of the sun, et cetera, et cetera. Okay, so this is interesting because if we take X-ray pictures of other galaxies, so this is a different galaxy, it's actually called the antennae, but this is a picture of that galaxy in the X-ray. It looks different from the picture of the optical, just like the picture of you guys in the infrared looks different from just looking at you. And there are some sources, these little point sources of X-rays, that are so bright that if this Eddington limit is correct, they have to be intermediate mass black holes. Okay. In fact, those of you who read the popular press might have seen this picture over the summer. So did anyone see this picture over the summer? Guess it's not as popular as I thought it was. It's not mine, it's somebody else's. But this source actually in another galaxy called ESO 243-49, it's 249 million light years away, but this is an artist's conception, not a picture, and there seems to be an X-ray source associated with this galaxy that would require an 8,000 solar mass black hole. There's actually a little issue with this because I don't think they've adequately ruled out that the source really is associated with the galaxy. It could be something in our own galaxy or something much farther away. Okay. Okay, but now, I didn't mean to go on. So now let me ask you a question. If I go back to this argument back here, I told you I can figure out how massive a black hole is by looking at how bright it is. But how could that get screwed up? In this picture here, I've assumed that the X-rays are coming out the same in all different directions. But can we actually check that? I mean, if I have a flashlight like this, and I point it right at Naomi in the front, who really likes... she'll think this is an extremely bright black hole. But how about someone over there? Now, okay, so I've assumed, making this assumption, we can only see the light that the black hole emits in our particular direction. Okay? But to go and do this calculation about the mass of the black hole, we've had to assume that that's the same coming out in every direction. Okay, so this actually then presents an extremely important question in the study of these, what we call ultraluminous X-ray sources or intermediate mass black holes. So the question is are the X-rays coming out of the black hole a beam like this, or do they come out equally in all different directions, just like a light bulb or like the sun? Okay, and what is that question exactly? What would you say? Any English majors in the crowd? Okay, I actually tried to get our Dale Stilley, our guy who sets up the demonstrations, to give me a skull at this point. That's a hint. Why would I want a skull at this point? What? A skull, a human skull, to hold in my hand and ask a question. Well, the question is, to beam or not to beam? Well, that groan was extremely satisfying, actually. Okay, so the question about these sources is, do they have uniform emission, light coming out in all directions? In that case, we're getting the luminosities right. So this Eddington argument should hold. Or do they have beamed emission? Okay, interestingly, this is actually a theoretically considered shape for these accretion disks of gas surrounding a black hole. And guess what the name for that particular theoretical model is? Yeah, a donut, but what kind of donut? It's actually called a Polish donut. That's the technical term. The name was invented by a pair of Polish theorists. So. Okay, so let me ask you a question there. If we can only see the black hole in one particular direction, is there any way we can tell whether or not the light's beamed? Someone says no. Someone is either raising his hand a tiny bit or scratching his head. No, okay. Well, let me remind you what the problem is. If I take the flashlight and point it at you, you could see we've already picked out an X-ray source which is very bright. Okay, now I'm going to point it at everyone who's asleep. The question is there also light coming out in this direction? So is there any way that you could tell whether or not there's light coming out in this direction? Okay.
Can you prove that gravity bends light? So like in the 1919 experiment, the light that was coming around the sun from the stars made them seem out of position?
Yeah, but only by a tiny amount, by arc seconds, which like 1,000th of a degree, and a degree is only, well, my thumb is 2 degrees held out to my arm, so the light bending there is a tiny amount, and here you would have to bend the light by, 90 degrees. Okay, but it might not rotate. But if I take my laser pointer like this, if you couldn't see the little spot over there, I mean, there isn't a convenient screen over to the side of all these black holes. But is there any way you could tell? Something passing in front of it. We're getting closer. A satellite going around. But yeah, that won't tell us about the light directly, but that would be a great way to measure the mass. There's someone pointing over there. Okay, go ahead. Yeah, that would be good, except the black holes we're talking about are millions of light years away. So you'd have to have the second telescope in some other galaxy, which is also a few million light years away, which I would love to do, but we haven't done it yet. Anything else? Yeah, but then you'd have to put it on a different planet, on a different galaxy. Okay. Well, let me ask you another question. You ever drive in the fog? You ever drive at night and you can't actually tell whether or not your lights are on? But then you go into the fog, and suddenly you can tell whether your lights are on? So now you can tell that there's a beam going off on this side, right? Well, you couldn't if there wasn't anything there. Okay? So astronomically, what we want, clouds of dust, astronomically, or clouds of gas, are nebulae. So what we want is to find one of these ultraluminous X-ray sources sitting inside of a nebula. And then we just ask the question, well, does the nebula get lit up by just one little spot right in our direction? Or does the nebula get lit up in all different directions? Okay. And actually, there were two Frenchmen, Manfred Picul and his graduate student, who found a nebula in the galaxy called Homburg 2, surrounding a source called Homburg 2 X1. And a few years after we found it, Manfred actually, for some reason, doesn't like using the Hubble Space Telescope. But so it fell to me to actually use the Hubble to take a picture of this nebula that we found over here. So the X-ray source sits right in the middle there. And we took a picture using the Hubble Space Telescope, not with X-rays, but in a special line produced by helium atoms only when they get struck by an X-ray. Okay, so this particular type of radiation coming out of helium atoms, to form it, you have to have an X-ray hit the helium, and then as the atom recombines, it actually takes out this, it emits this particular color of light. So this particular color of light is telling us which parts of the nebula are actually being lit up by X-rays. And what does it look like? Well, the question, if the radiation from the black hole were beamed, we would see a little dot right in this particular direction. If the beam coming out of the black hole were a laser beam, like coming out of this, it would be pointing right at you. I don't actually want to blind anyone by pointing it at you. But what we would see in terms of the nebula would just be a nebula that looked like the one I showed here. It would be a long cylinder pointed right in our direction. It would be just like a little dot on the sky. But what we can see instead is that the X-rays actually come out in lots of different directions. They light up the nebula in lots of different directions. And therefore, it looks like the X-rays are actually coming out in a broad way. Okay, and actually, numerically, we can use this picture of the nebula to figure out what the true luminosity in X-rays is, and it turns out that it's pretty close to what we would estimate directly. Okay, oh, and sorry about the use of the word ULX here. Okay, so that's one indirect indication that we really have these other these intermediate mass black holes. So let me ask you another question. I asked you before if you could tell something was moving or not without seeing it. I don't tell anyone, well, okay. Which of these two things is bigger? Everyone agree the first one was bigger? Why? Yeah, the kid actually had my next line there. Good job. You should be a scientist when you grow up. The one who called. Okay. Larger objects vibrate more slowly. Okay. The same is true about objects even as odd as accretion disks surrounding black holes. Okay, I originally actually, this is supposed to be visually suggestive of an accretion disk. Does that work? Okay. But it doesn't seem to have completely worked. The same thing is actually true. So now let me let you listen to a couple black holes. So first we're going to listen to a black hole called GRS 1915+105 that my friend Ed Morgan from MIT actually took observations of this object in X-rays. Okay, and then the X-rays, the intensity of the X-rays actually changes as a function of time. Okay, so he measured how much the X-rays vary as a function of time and translated that into an audio file on his computer. But in order to hear anything, he actually, he sped it up by a factor of 100. I sped it up by an extra factor of 6. So totally, it's a factor of 600 times faster than what we actually see on the sky. And it sounds like this. Okay. Now, I took some observations of an object called M82X1, which is one of these potential medium-sized black holes. Unfortunately, it's so far away we don't get enough photons that we can directly convert it to sound. But I analyzed the frequencies that we see in the X-rays and then produce sounds at those same frequencies. Okay, it sounds like this. Could everybody hear that in the back? I'll turn it up just to make sure. So which black hole is bigger? Yeah, not me. Okay. But this object here oscillates slowly. The accretion disk around that black hole actually oscillates. It rings literally like a bell. And the frequency that that bell rings is proportional to the size. And the size of an accretion disk around a black hole is actually proportional to the mass of the black hole. Bigger black hole or more massive black holes are literally physically larger. It's actually a linear proportionality. Okay? And the fact that the frequencies coming out of that black hole are lower suggests that the black hole is actually quite larger. In fact, if you do it numerically, those frequencies suggest a black hole mass of around 400 to 1,000 solar masses. There's another object, which I like to study also along with our colleague Cornelia Lang, also in the physics and astronomy department, called NGC 5408X1. It shows even lower frequency oscillations. In fact, found by Todd Strohmeyer of NASA Goddard Space Flight Center. Those suggest a black hole of a few thousand solar masses. It's a very low frequency. In fact, on the previous page, I actually first tried to make a sound file of this one, and I could never hear anything until I realized that the frequency was just below what you could hear with a human ear. So that's very suggestive that there's this big disk that's oscillating slowly. So it's another piece of evidence in favor of their meeting these medium-sized black holes. This is actually a Chandra picture of the center of the M82 galaxy. The black hole in question is this one right here. These are taken at 2 different times. This is actually the center of the galaxy. The important part of this picture actually at first was to prove that that object wasn't in the center of the galaxy. Okay, this is actually a plot. Oh, I lied. This is the second plot, not only one. Of the total intensity of X-rays coming out of M82, and you can see that it goes up and it goes down and it goes up and it goes down and it goes up and it goes down, and it keeps doing that. We didn't observe here because it took us about that long to figure out that this was going on, and we asked for more observations. But every 62 days, the intensity of the black hole goes up and goes down and goes up and goes down. This is too big to be caused by the disk of the black hole, but it's probably caused by the star orbiting around. And it looks like that 62 days comes because the star orbiting around actually orbits once every 62 days. And from that, you can actually calculate what the star has to be like, and it has to be something called a giant or a supergiant star, which is very interesting, coincidentally, because that's just the kind of star you need. A normal star can't feed a black hole fast enough to make it as bright as this object should be. But a giant star can. Okay, and the last thing is, if you remember in the beginning, I told you that these one place that people wanted to look for these intermediate mass black holes was in globular clusters. Well, baby versions of globular clusters are something called superstar clusters. That's a globular cluster just when it's forming. Okay, and this X-ray source here, well, we don't know the position exactly, but it's somewhere within that blue circle. And right there's actually a superstar cluster called MGG11. And some people in the Netherlands, Simon Portegues-Wort's actually done simulations of that star cluster that show that it should form an intermediate mass black hole at its center because it's so dense at its core that the stars actually physically collide with each other. Okay? And so you can build up a 1,000 solar mass object by colliding, 50, 20 solar mass objects. And the cluster is only 11 million years old, but it's had enough time that a lot of collisions are expected to happen on the inside. So again, we have indirect evidence that this object could be, case is getting better, that it could be one of these medium-sized black holes. Okay, so we've approached 8 o'clock. So I'll just put up my conclusions. Okay, so if you've learned anything, you should know that black holes are common throughout the universe, and we know of two sizes of them. Ones around the mass of our sun and supermassive ones that are found at the centers of galaxies. The next important lesson was that the formation of galaxies is intimately linked with these supermassive black holes at the center in a process we don't understand. Okay, and then the final thing is that we haven't really proved yet that they're these medium-sized black holes, but we keep getting better and better and better evidence that looks to indicate that at least we found a few examples of this. Okay. And then my title was Black Holes of All Sizes, and I didn't realize that I didn't actually say anything about black holes as smaller than astronomical ones, so I just put in a joke to you. Okay. And then there'll be cookies after that Steve will put out, so thank you.